Folks, and welcome back to Physics with Captain Rod. The purpose of this video here is to help demonstrate how to apply energy concepts to a problem in mechanics. So in this example, picture this mass right here. I'm going to call that mass A. Mass A is 20 kilograms. It's attached to a rope which goes over this pulley and down to here to mass B, where mass B is 10 kilograms. And imagine that the system is allowed to accelerate from rest under conditions where there's no frictional force acting on mass A. And what we're going to do here is try to calculate ultimately how long time-wise it's going to take for mass B to hit the ground. And while we're at it, we're going to also calculate maybe the acceleration of the system and the tension in that rope. So we're going to start this using principles of work and energy. And to apply work energy principles, the work energy theorem is a theorem that relates different states. So here's what we mean by state 1, all right? Mass B is right here. So I'm going to call this position 1 for mass B, and here's mass A here. I'm going to call this position 1 for mass A. And then what's going to happen is that the system's allowed to accelerate, right? I'm going to use my motion diagram here to kind of illustrate mass B is accelerating. So position 2 is going to be here just before it hits the floor. And this velocity vector that I drew, this is going to be the velocity of particle B, picture 2. Mass A will have moved over to the right. So here's the new position for mass A. I'm going to call that picture 2. Mass A is moving to the right, and I'm going to call that velocity VA2. So work energy theorem is about changes in state. So this is kind of the change in state here. Position 1 is here for mass A, here for mass B. This changes to a new position, position 2, which is here for mass A, here for mass B. In addition to that, there's a velocity vector now in position 2 for both masses. I'm going to go ahead now and write out the work energy theorem, which says PE1 plus KE1 plus work from 1 to 2 is equal to PE2 plus KE2. So in order to use this theorem now, we're just going to go through and evaluate this term by term. Now, to deal with potential energies, we have to define a datum. I like to use the lowest point in the problem for my datum, so I'm going to go ahead and just make this line right here my datum. This is where we measure potential energy from. So as far as mass B is concerned, it has a potential energy equal to mgh. I'm going to go ahead and call that 3 meters h. So we're going to have mass B, g times h for the PE1 term. Now, mass A is above our datum by whatever this height is, from here to here. And whatever that height is, it's not changing. It's the same height here in position 1 as it is here for position 2. So if I decide to put a term in for mass A, it's going to be an mgh term, but the h isn't changing, so I'm going to have exactly the same term under the PE2 here in the work energy theorem, and that term's just going to subtract off. So I'm just going to ignore mass A. It's not important for the problem. If you want to put an mgh term here for mass A, go ahead, but just keep in mind you're going to have exactly the same term here, mgh, and they'll just subtract off anyway. All right, now next, the kinetic energy terms. This system starts from rest, so KE1 for mass A, 0, KE1 for mass B, also 0. The work term in this problem is 0. I'm going to just write the 0 for now, and I'm going to come back and talk about why here after I get the other two terms completed. All right, equals, all right, PE2. All right, now we've already considered mass A, nothing to worry about there. Mass B is now at our datum, so it has no potential energy, so the entire PE2 term is 0. And now we'll talk about the KE2 term. So at position 2, mass A is moving to the right, so it's got a kinetic energy of 1/2 its mass times its velocity, VA2 squared. In addition to that, mass B is here moving down, so it's got a kinetic energy of 1/2 mass B times VB2 squared. All right, I'll get to the velocities and how we deal with that in a minute. I want to go back and talk a little bit about the work term. So the work term, right, in a work energy theorem, this is for forces that are external to the system and forces that are non-conservative in nature. This is for forces that change the net energy of the system. If If we think about the different forces acting on this system, okay, let's look at mass B. If I think about the free body of mass B, there is in fact a gravitational force that points down. If I try to put a work term in, that term is going to equal force, mg, times the distance, h. So, and keep in mind that the mass would be mass B. So the actual work term, if I put a work term in for this force, is going to be mass B, g, times the height, h. And you'll notice that that's exactly what we have right here. So in effect, when we use a potential energy term, we're already taking gravity into account. If we take it into account again, we're going to be double dipping. The other force that we need to consider here that's acting maybe on mass B is this tension. So there's a tension up. If I calculated a work term for it, for mass B, right, force is tension times distance, I'm calling that h. However, the force is up and the velocity vector is down, so the work term is negative. So minus th would be the work term for mass B. Now, if I do that and I come over here now to mass A, there's a tension to the right. It's the same tension. If this is a reasonably good pulley, it's not frozen shut. The work term for mass A would be equal to the tension times however far mass A moves. Now, if mass B moves down 3 meters, mass A also going to move 3 meters. That's the distance I'm calling h. So the work term on mass A is positive t times h. You'll notice that if you add these together, you end up with 0. The tension in this example is an internal force to the system. If I wrote a work energy theorem for mass B only, I would definitely need to include the work done by the tension. Or if I write a work energy theorem equation for mass A only, I would have to include a work term for the tension. But considering them at the same time, that force is an internal force and doesn't need to be considered. So, let's see, other forces to consider. There's a normal force acting on mass A, which is up. That doesn't do any work because it makes a right angle to the velocity of mass A. There's a gravitational force down. That doesn't do any work, as in this example, same argument, the right angle argument. If it did do work, we would already have a potential energy for it anyway. So all forces are considered acting on the system. I think we're good to go here. So that's why the net work done on this system is 0. In general, with this term, this work 1 to 2, you're looking for external non-conservative forces that are changing the energy of the system, either adding energy to or taking energy away. So we don't have that. Oops. In this example, we're pretty well done. So the next thing to do here is go through and just put in numbers and calculate the V's. Now I would take note of this, that if mass B moves 1 meter, mass A also moves 1 meter. If mass B moves 3 meters, mass A moves 3 meters. As long as this rope doesn't stretch or break, the distance that each moves is the same, and these velocities also are the same. So I'm going to take note that VA2 is the same as VB2, and I'm just going to call that V2. If we put in the numbers into this equation and solve for V2, I get 5.9 meter per second. So mass B is going to hit the ground traveling at about 5.9 meter per second. Now, nice thing is work energy equations tend to be nice, easy equations. They're usually fairly easy to solve, like in this example. Now that we know the velocity here, now what we can do is use it to help us study the motion of this system. So I'm going to go ahead and maybe study the motion of mass A. I'm going to put a coordinate system right here, pointed this way, plus x. And I'm going to draw a velocity graph for mass A, taking note that it starts from rest, so this graph would go through the point 0, 0. Velocity is increasing up to a point here where we know its velocity is going to be 5.9 meter per second. After some time, we don't know yet. But what we do know is that the velocity will be 5.9 meter per second after mass B has moved 1 meter and mass A also has moved 1 meter. So I'm going to go ahead and use this graph to write an equation for the displacement of mass A. Keeping in mind this is a velocity graph, so the area under the curve here is going to equal the displacement. So I know that is 3 meters equals, and because this is a triangular area, we can write this as 1/2 t times 5.9 meter per second. I can go ahead and solve this for t. Let's see, and I get about 1.36 seconds. Now, since I have the graph right here, I might as well calculate the acceleration right away. Remember these graphs, there's two important properties, slope and area. So for a velocity graph, the area gives you the displacement, the slope gives you the acceleration. So the acceleration of the system here, right, rise over run, 5.9 meter per second in 1.36 seconds. And this is approximately 3.2 meter per second squared. So now we know the final velocity, we know the time it's going to hit the ground, we also know the acceleration of the system. So let's see, we got that. All right, now I'm going to work on finding the tension in this rope. We can get that one of two ways. We can either draw a free body of mass A or a free body of mass B. I'm going to go ahead and draw my free body of mass B. I'm going to do that right here. So imagine, here's a free body mass B. There's two forces acting down. We got a gravitational force, mg down. Now keep in mind that that's mass B. This tension acts up on mass B. I know that the gravitational force, the mg, has to be more than the tension because the acceleration direction is down, therefore the net force is down. So here's our free body. Remember that forces come in two types, field forces and contact forces. Gravity is a field force, and then the only thing in contact with mass B here is the tension, or the rope here, creating that tension, and nothing else if we throw out air drag. So the free body's done. Next thing to do is write a Newton's second law equation for the free body. My standard rule of thumb is to identify the acceleration direction, call that positive. So when we write our Newton's second law equation, sum of all forces equals ma. Because I can observe that this is accelerating down, I'm going to go ahead and put down positive. So the equation we're going to write is going to be the weight, mg, keep in mind it's m sub bg, minus t, and that's because, again, I'm doing down positive, but the tension is up, equals mass b times a. And the last thing we need to do here is just go ahead and solve this for t. And I get m sub bg minus m sub ba. And now I'm just going to calculate a numerical value. It's just going to take me a moment to do that. So mass b, give me a minute here, I got to use my phone and fire up my calculator, is 10 kilograms. And I get about 66 newtons out of this for the tension acting on mass B. Now, we should get the same thing with a free body of mass A. Just a quick look over here to the right. The only force acting in the horizontal direction on mass A is the tension. There's a gravitational force acting down, normal force acting up. I'm not even going to bother putting them in the free bodies because this is the only one I need because the acceleration is to the right and the other two forces are vertical. So basically we would have net force equals m, which is 20 kilograms, times A, which is 3.2 meter per second squared. And I'm just going to put the units out here. Kilogram meter per second squared is a unit. And that multiplies out, I think, to 66 newtons. So we're pretty good shape here. Hope you enjoyed the video. Have a great day.